Welcome to the WITS workshop on linear algebra in data science. I'm Margot Gerritsen. I'm a professor at Stanford University and co-founder and co-director of Women in Data Science and your instructor for these 40-some minutes. Why a workshop on linear algebra? Well, first of all, I love linear algebra. I fell in love with it when I was in college about 40 years ago now, and I still love it. But really, it's because when you look at data science algorithms, you look inside, you see that many of the building blocks of these algorithms are, in fact, based on linear algebra. So if you want to build tools, or if you want to understand the behavior of algorithms better, understanding linear algebra is just really great. Now, of course, we cannot do justice to linear algebra in just over 40 minutes. So see this workshop as a little appetizer, a first impression, hopefully making you hungry for more. We will touch on some of the most fundamental concepts in linear algebra. I'm not assuming any prior knowledge. This is not an advanced linear algebra workshop. All I will assume is that you've worked with two-dimensional vectors a little bit. We'll use examples from data science, searching, ranking, a little bit of compression, and we'll use those to motivate all of these concepts that we're talking about. And along the way, you will get to know vectors and vector operations and matrices and matrix operations. And at the very end, I'll touch very briefly on the incredible singular value decomposition, which is often referred to as PCA, or principal component analysis. And the reason I'm doing it is that I often find that data scientists who haven't studied linear algebra become interested in linear algebra when they get to PCA. So maybe we'll end with that, and you'll get a little taste of that too. But we're going to start with an example that is based on an activity that you no doubt have done recently, and that is searching on the internet. So let me share my screen here with you. Here I'm searching for women in data science, and to my surprise, within a second, 0.71 of a second, I get several million results returned to me that relate to this topic. And not only are they all collected, but they're also ranked. Now, how is this possible to do that so quickly? Not just finding relevant pages, but also ranking them. To see that, we are going to shrink the internet, and I'm going to shrink it to 5 pages. And I'm going to shrink the dictionary to 4 words. I know it's totally crazy, but at least then everything fits on one slide. So the first page has the words Stanford beating California. And for those of you who know about the friendly rivalry between Stanford and the University of California in Berkeley, you will understand this choice of words here. The second page has 2 words, beating eggs. The third has 1 word, egg. And the fourth and the fifth also have just 1 word each. Now we're going to summarize this whole internet, so those words, where they occur, and the web pages in a table. And every row of the table corresponds to a word, and every column of the table corresponds to a page. And if a word is in a page, we put a 1 on the corresponding element of the table. If it is not, we put a 0. This table is often referred to as the term document table, where term stands for word and document for page. Now here our term document table is really nice and small. And in reality, of course, this table had billions of columns for all the web pages in the world. And also a lot of rows, because in the English language alone, there are about 200,000 unique words. And then in the dictionary, in this term document table, we'll also include conjugations of those words. We'll include bigrams like New York, common misspellings, and slang, and so on. So billions of columns, probably a few million rows. Now with this table, we can now create a digital representation for each web page, right? Because every web page now corresponds to a sequence of 1s and 0s indicated here. Now, the nice thing is that when we're searching for something, we can also express the search phrase as a sequence of numbers. We can see the search phrase, in fact, as sort of a mini web page. So suppose we're searching for the phrase Stanford eggs, then Stanford eggs we could write down as a sequence 1001 because it contains just the words Stanford and eggs. So when we're searching and we want to find relevant web pages for a search, what we're really asking is which of the web page sequences are closest to the search sequence. And to do that, we use vectors. Okay, so we're not going to do this on sequences like this, but we'll translate this into vectors. So let's go and look at some vectors now. And I'm going to change to my favorite tool, which is a document camera. Okay, and we're going to be writing some of this stuff down in the old-fashioned way. Now, you will probably have worked with some vectors before. So here's a two-dimensional vector x, a over b, another one y, c over d. We can do all sorts of things with vectors like this. We can compute the length of, say, x using Pythagoras. Remember that theorem. And the length of the vector x is then just the square root of a squared plus b squared, the square root of the sum of the squares of its elements. We can also compute an addition. We can take x and add it to y, either through this parallelogram construction or just by adding up the coordinates. Now, in 2D, I can define a vector, and I can do this in 3 dimensions also, and I can't really visualize vectors in 4 dimensions or higher dimensions, but I can abstractly understand that because a vector is like a sequence of numbers. So let's go to this search vector or the search sequence that I saw for Stanford X. You know that that corresponded to the sequence 1001. So we could store this in a vector that lives in 4 dimensions, 1 for every word. 1, 0, 0, 1, 1 above 0, above 0, above 1. Now, of course, we could expand this and we could say, hey, we can think of a dream of vectors in any number of dimensions. This is what it would look like in n dimensions. Now, of course, in n dimensions, I'm not going to use coordinates like A, B, C, and D because I quickly run out of letters in the alphabet if n is very large. So instead, I refer to elements as x1, x2, and so on, all the way to xn using that little subscript there. Now, if I have vectors like this in any dimension, I can also do things like adding those vectors together, just as I did in 2D. So really nothing much changed there. I can also extend Pythagoras. Now, when I do that, I get something like this. So the same form as Pythagoras for 2 dimensions, but now for multiple dimensions. By the way, this symbol here is the symbol for magnitude that we often use in the field, 2 double bars on either side of x. Now, we know how to do a little bit of vector algebra because we've just said that we know how to add vectors together. Could we, like we can do with scalars, multiply vectors, for example? Now with scalars, it's you know how to do that, but with vectors, how could we define this? How could we define this algebra? Okay, so let's think about vector multiplication. Now maybe you're tempted to design something like this. You say, here's an algebra, x times y, I define like this as a vector with every element just a product of the corresponding elements of the vectors. Now, it turns out that this type of algebra is not very useful. And instead, what we use a lot is a different kind of product called an inner product, or sometimes called a dot product. And it's defined this way. That looks a little different. So again, we are computing the product of elements, x1, y1, and x2, y2, but now we don't put them in the vector, but we add them all up. And this is then just one number, right, that we call the inner product or the dot products. You will find some other notations for this too. Here are some common ones. Instead of x dot y, you could also write it like this, where x, the first one, is written as a row vector and y as a column vector, like this. And that x as a row vector is like we took x, that vertical vector, and we flipped it around to become horizontal, and that flipping operation is done by taking what we call the transpose. That is what that superscript t stands for. So you will see that notation later as well. Now, this inner product is unbelievably important. In fact, it is the most computed entity in the whole world. Every second, as I'm talking now, billions of inner products are computed on computers around the world. And there are whole computer architectures that are designed to do fast inner product calculations. Why is that? Well, to see that, first we need to get convinced that this inner product is actually pretty useful. So let's do a little bit of algebra with it. The very first thing we could do is compute the inner product of x with itself. And when we do that, we actually see that that's the magnitude, the length of x squared. Now, the other really interesting thing is that there is such a thing for vectors that is called the cosine rule. And you may remember the cosine rule from trigonometry for triangles in 2D. But we can do something similar for any vector in any dimension. If I have two vectors, x and y, and the angle between them is theta, I can show that the cosine of that angle theta is given by the inner product of x and y divided by the product of the magnitudes of these vectors. But remember that the magnitudes of these vectors through this relationship is really also an inner product calculation. So this is what an angle looks like. Now, why are these inner products used so often? It's because of this, because we compute so many angles between vectors. And to see that, let's go back to our slides. Okay, hello, that's me again. So we go back to our slides. And remember that we were searching for these blue sequences that were closest to the red sequence. But now we know that we can look at the sequence like this as a vector. Now, I cannot draw 4D, but it can give you some sort of artistic impression. So here is it. Here are the 5 vectors, the blue vectors representing the web pages, and the 1 red vector representing the search vector. And we want to return those blue vectors that are closest to this search vector in our search, right? And to do that now, we have a tool, because what we could say is close means that the angle between those vectors is small. So for every blue vector, we compute its angle to the red vector, so here theta, and then we return the blue web pages that are pretty close. And usually we use a threshold angle for this. Okay, and that is what the search engine does. So all these results that you're seeing are all web pages whose vectors are within a certain angle of the search vector. All right, now, and then we know that to compute these angles, we have lots of inner products to compute. Okay. Now, remember that the term document table we had was really massive, and that not only do we have a tremendous number of web pages, we also have many, many, many words in them. So the vectors that we're computing in the products for are many, and they are very long. So if you look at a quick back of the envelope calculation, and you say, okay, in order to search for a phrase in the internet, we have to compute billions of inner products on vectors that are millions long, you will quickly find that even with the fastest computer in the world, you will never get all those results back to you in under a second. And then we haven't even ranked the pages yet, which is also a really expensive calculation. So clearly, search engines do more. They make these inner product calculations much, much faster. And to find out how they do that, you need more algebra. So maybe if you're interested in this, this is one of the reasons why you're going to dive in deeper into linear algebra after this workshop. Okay, but now it's time to move from vectors and introduce a second linear algebra structure, which is called the matrix. And we've seen one already, but we called it a table. So we looked at this term document table. Now the essence of this table are really those numbers. So let's isolate those numbers, and we're going to put some brackets around it, and we're going to give it a name. And for matrices like this one, we call this a matrix. It's like a table of numbers with brackets around it and has a proper name. We use often capital letters to give it proper respect, right? Scalars are often indicated by lowercase letter, matrices with capital letters because they're important. So we've seen matrices, and we see this particular matrix or table stores information. Here's another matrix that stores information. This is a matrix that stores information about a black and white photograph. This photograph has 36 pixels, 6 by 6. And in the matrix, I put a 0 if the corresponding pixel in the photo is white, and a 1 if it is black. And I can set up matrices that store color photos as well. I just need more than one matrix because I need to store more than one color. So apart from starting movie franchises, the matrix, matrices are obviously used to store information. But where else do they come up, and what kind of algebra can we define for matrices? Can we multiply matrices? Can we play with matrices and vectors? And the answer is yes, and there are really useful ways also to define such multiplications, and they come most naturally in the next application of matrices, and that is representing linear systems of equations. And the application we're going to look at to introduce linear systems is a web page ranking. So we looked at these web pages, and we get them all collected, all those web page vectors that are within an angle around the search vector, but they're also ranked. And you may think, well, why don't they just rank them according to this angle? But you know, the ones with the smallest angle may be obscure or old or not very popular, and that's not what you want. So you really want to rank based on many different criteria. And in fact, apart from the angle we just calculated, there are many, many factors that they take into account when they do this ranking. The number of visits, the recent edits, the age of the page, the angle we talked about, and also something called the traditional page rank. And that is what we're going to study next, because it's such a nice algorithm, and it's applied not just to page ranking, but also many other ranking methods in data science. Now, the original PageRank algorithm was developed by the Google founders, Sergey Brin and Larry Page, in the late 90s, and that was done at Stanford campus. And they wrote a lovely paper about this. How did they do this? At that time, and I will illustrate that using these web pages, there wasn't much user data. So you couldn't really use that for ranking. So what they come up with was something that just depended on hyperlinks. So you can see the internet as a network of web pages that are all connected through hyperlinks. You have outgoing hyperlinks on a page that you can click on to hop to another page, and pages have incoming links because other pages link to it. So here is an example. Here's my website here, and I've got an incoming link from my own Facebook page, and I have an incoming link. In fact, I had a while ago from a media company called KQED that at some point linked to me, and that made me feel very chuffed. Now, the first idea of this traditional PageRank algorithm is that you are more important as a page if you have more incoming links. So that's a measure for popularity, so that makes sense. So KQED, public media, probably has many, many, many more incoming links than I have. So obviously it's a more important page. So that's idea number one. The more incoming links, the more important you are. The second idea comes from this fact that if you get an incoming link from a popular page or an important page, that should weigh quite heavy. So I said, I was chuffed when KQED linked to me. I felt important because an important page was linking to me. So it makes sense that when we're creating a model, that incoming links from important pages are weighted heavier. But wait a second, we got to be realistic, because I was certainly not the only one linked to by KQED. So I may feel great, but if KQED was linking to a million other pages, my importance really wasn't that great to speak of. So the third idea is that the weight of an incoming link should again be weighted by the number of other pages I share this importance with. Now, it's nice to talk about these three ideas, but how do we actually create a mathematical model for this? And the way we do this is by creating a little example internet. So let's go to this tiny internet. It's got 6 pages, numbered 1 through 6. And here is the network of those pages where you see the outgoing links and the incoming links. For example, page 1 links to 2, 3, and 4, etc. Now we're going to set up the importances of all of these pages, and we're going to put those importances, the ranks, in a vector x. x1 is the rank of page 1, x2 the rank of page 2, etc. Now, what is then the rank of page 1? We said that we would measure the importance of a page through the number of incoming links, but guess what? Page 1 doesn't have any, so it's a little pitiful. And then the rank should simply be 0. So x1 is 0. Now that turns out to be pretty nasty because it will collapse the whole system, but we'll talk about that later. Now, how about page 2? So page 2 has an incoming link from page 1. Now, ignoring that x1 is 0, we would normally say, okay, then page 2, its rank should be impacted by the rank of 1. And the way we model this is through so-called rank propagation. In fact, we're going to share the rank of page 1 across all of the pages page 1 links to. So I'm going to take x1 and I'm going to give page 2 a third of it, because there are 3 pages that page 1 links to. So the fair share for page 2 is just a third. So here I get x2 equal to a third x1. So now I can continue and I can set up the other equations. For example, to find x3, the importance of page 3, I see, okay, it gets a third of 1 and it gets a half of 2 because page 2 shares its importance with 3 and 6. Okay, so here are the weights on those propagated ranks, and you see them adjusted for various places. And this is then the system of equations that we get out. x1 is 0. Now, unfortunately, as I said, this collapses the system because this means that x2 is 0, this means that x3 is 0, and x4 is x5, and x5 is x4, and x6 is 0. And that is not very meaningful. So clearly something needs to happen. And the problem, of course, here was that x1 did not get anything. So what Sergey and Larry did is find out this model. So that was one contribution. They then realized that to find solutions to this that were meaningful, they actually had to sort out a few problems that this had. And this is one problem, that some web pages may not have incoming links, and you have to adapt for that. But ignoring that, leaving that to the Google founders and leaving that to that report, what we get when we look at this is a coupled and linear system of equations. So clearly, systems of equations come up a lot in data science, and ranking is just one of those examples. So how do we deal with system of equations, and what sort of algebra do we need for it, and how do matrices come in? Now, to see that, we're going to look at a smaller example, and we're going to go back to our paper and do that on paper. All right, so you can take just a little stretch here while I switch over to my document camera. All right, so the system we're going to look at is a cute little 3x3 system here. 3 unknowns, x1, x2, and x3. Let me just make sure that this is in focus. Okay, maybe it's a little bit better. x1, x2, and x3. Okay, and here 3 equations. And for the fast people amongst you, who maybe done this a little bit before, maybe you can spot that the solution to this is actually x1 is x2 is x3 is 1. But we want to see how matrices come into play. To do this, we're going to rewrite this equation a little bit. The first thing we're going to do is just write it neatly, okay, instead of sloppily like this. So we're going to put all the x's under each other. The second thing is to make sure that all the gaps that we see here are filled. And then to make sure that the structure of each equation really is all the same. And the structure I'm looking for is that every equation is going to be something times x1 plus something times x2 plus something times x3 is equal to something. Now, you may recognize already here that that is an inner product. It is an inner product of the vector x with the vector with elements 1, 1, 0. Remember that. The same for the second row and the third row. And everything has this plus, just like we do with inner products. So if it was a minus x2 here, it would be plus, and then the coefficient would be minus 1. Now the coefficients are indicated in red, and you can probably see where we're going. We're going to store these coefficients, which really give us every information we need about the system of equations in a matrix, the matrix of coefficients. And we call that matrix A. Okay, so this is the matrix A. We store the solution, of course, in that little vector x. We use the vectors now. We store the right-hand sides all in another little vector. We call that B. We now say, and this is where matrix vector multiplication gets defined, that this equation system here can be recreated by multiplying A with x. This is how matrix vector multiplication is defined. So when you multiply a matrix with this vector, you can recreate this system. So we're going to put a cross here for matrix vector product and an equal sign there. So really what we're doing is creating the system A times x is equal to B, okay, like this. And how does this matrix vector product then work? Well, we already gave it away here. We see that that first equation is the inner product of 1, 1, 0 with the vector x. It's the inner product of the first row of A with the vector x. So that is how I do the first step in matrix vector multiplication. The second step is to go to the second row and compute the inner product of that row with the vector. I get this equation back, and the same for the third row. So now we know how matrix vector multiplication works, and that systems of equations can be written in this form AX equal to B. Now, we can write as AX equal to B. Now, of course, the question is how to solve this. In solving these systems, AX equal to B is a huge topic in linear algebra. And this comes up all over in data science and other engineering applications. And sometimes you can solve fine, sometimes you cannot, sometimes you have to approximate solutions. For example, when you do linear regression, if you're maybe familiar with this. But in any case, AX equal to B is unbelievably common. I've worked on many different applications in my life, from sail design to reservoir modeling to wind turbine placement optimization to search engines. Really a lot of different applications, and it seems really weird, to have a career that spans so many different application areas. But the thing is that all of them have in common that ultimately, once you've translated things into mathematical models, you have to solve a matrix vector equation. So now we know two uses for matrices. We know that it can store information, and we know that it can represent systems of equations. There is a third one, And that third one is the one that is going to lead us to the next bit of algebra, and that is the matrix multiplication. So, right, we know how to multiply vectors with the inner product. We know how to multiply matrices and vectors, but what do we do with matrix multiplication? And it's much easier to understand this when you know that matrices can be looked at in a third way. Not a storage system, not representing system of equations, but something else. So let me explain what that is. So we are going to first look at a very simple little matrix vector multiplication. Okay, we know now how to do this. We have A, we know X in this case, and when we multiply them out, this is the B that we get. So graphically, we could look at it like this, right? We have X, and X is transformed into B after we apply A to it. Okay, so we hit X with A, and we get a new vector B, and B has a different direction and has a different magnitude in this case. Now I can really start seeing these matrices then now as operators. I have X, I apply A to it, and I get a different vector B. What kind of operators are popular, and what kind of operators can we think of that can be represented by matrices? Well, how about rotation of a vector? Okay, so here is a matrix that gives you a rotation of a vector about the angle theta. So the matrix is given in this form: cosine theta minus sine theta, cosine theta. And if I take a vector now and I hit that vector with this matrix R, then the result of it is that X will be rotated by theta. And you can play with this and convince yourself for different thetas that this is indeed the case. So this is a very, very popular and well-known operator, a matrix operator. Now here's another one, and that's projection. So one of the simplest forms of projection is if we project a two-dimensional vector onto the x-axis. Basically, what we do with this is we set the second coordinate of that vector equal to 0, and the first coordinate we leave unchanged. And that can be done by multiplying that vector by a matrix P for projection, that looks just like this. Okay, so if you think about it, if you multiply this by X, it does exactly what we wanted. So now to illustrate how matrix multiplications come into place, what we're going to do is look at the combination of these operators. Because I could do, for example, first a projection and then a rotation. So let's see what comes up then. And what I'm going to do is look at rotation after projection for a general X. So the very first thing we're going to do is apply the projection. So I compute Px, and as I said, when I project onto the x-axis, the second coordinate is simply set to 0, and the first one stays the same. And this is exactly what this matrix vector multiplication does. Now we take this result, the Px, and we now hit it with R. So this is R, the rotation after projection. So we take R and we multiply that result, Px, with R. And what we get is this vector right here, cosine theta times x1 and sine theta times x1. Now the interesting thing is that we could also get the same vector by multiplying X with this matrix. So if we had this matrix and we multiply X with this, we get exactly this. So this matrix represents this operation of R after P. Now this matrix is now defined as the multiplication, the product of R and P. So in other words, R after P is translated into R times P, where the times here is a matrix product. And that is how that algebra is designed. So what we want is if we take R and we multiply that by P, so we get R times P here, then we get this result of R after P. So this times this should be that. Now, what is that times operation then? Well, in fact, it's really very much alike matrix vector multiplication. What we do is we take the first row first, and we create the inner product of that first row with the first column of P. First row, first column, inner product, we put that in position 1, 1. First row, first column, 1, 1. Then we take that first row and we take the inner product with the second column. And we put that in position 1, 2. First row, second column, 1, 2 position. Now we've exhausted all columns for that first row. So we go to the second row and we take inner products with the first column. We put that in the 2, 1 position, second row, first column. And the inner product of the second row with the second column, we put in the 2, 2 position. So matrix multiplications are just, again, a bunch of different inner products, one after the other. All right. Now, we can now do all sorts of matrix multiplications. Okay, so here's another example, and here the matrices are different sizes. But it's okay, because the number of elements in the first row and the number of elements in the first column, say, are the same. So I can compute an inner product between those two and put it in this location. And I can do something that's even maybe a little bit weirder. I can take very skinny matrices. This is a vector, as we've seen, but I can also see this as a 3 by 1 matrix, very skinny matrix. And I can multiply that by one of those flipped vectors we saw earlier. So if this is, say, X, well, let me go to another color because oh, this is also a little bit tired. All right, well, this is X. This could be Y transpose, okay, because it's a horizontal vector. So I used a little transpose to indicate that. And we see that if we do this multiplication, we actually get a matrix. So this is X, Y transpose. Now, this is not, therefore, an inner product. The inner product, example, Y transpose X, where we have row vector times column vector instead of column vector times row vector. That is just 6, totally different, depending on whether you have the row vector first or the column vector first. We're going to use that a little bit later. I want to finish this workshop with something that seems a big leap to go from what we've done so far to this. But the interesting thing is we can sort of understand what's happening with just the algebra that we have had. And what we're going to look at is the singular value decomposition, or the principal component analysis, which is huge in data science. Now, this did not come up really quickly. You know, it took a lot of people decades to work on this, okay? So let me just tell you what it is and then use some of the algebra that you already know to play with this, and then we'll see one example. All right, so I'm gonna go back to my document my document camera right here. So the singular value decomposition. And this is the idea and well, the knowledge. We know that this is true, that every matrix that we have can be written as a special product of matrices. And we write it as this. For every matrix, no matter what size, could have any m rows and any n columns, so it could be any arbitrary m by n matrix. We can always find matrices U, sigma, and V, so that A can be written in this form. Now there is this transpose here, and I will make it clear in a minute what I mean by that. But first, a little bit about these matrices. These are really special. The first matrix U is, I write it like this, where every column of U is indicated by this vector. Okay, so the first column is the vector u1 and so on. Now, all these column vectors are orthogonal. So that makes that U kind of a special matrix with special properties. V is similar. It's a different size. U has M columns, V has N. Now, if M is equal to N, so if I have a square matrix, obviously they're the same, but in general, they could be different sizes. But again, the columns of V are orthogonal. Now, we had this little transpose here. So what do I mean by that? Remember that the transpose of a vector means that we flip the vector from a column to a row. That's exactly what's done here. So V transpose is the matrix that is formed by taking all the columns of V, these columns, and flipping them horizontal and making them the rows of V transpose. So we can write V transpose as a whole bunch of rows, one after the other, and each row is V1 transpose or V2 transpose and so on. Okay, so that's U and V. We can find those, and at the same time, sigma is very special. Sigma is a diagonal matrix, meaning that it's zeros everywhere, apart from on the diagonal, so these positions, and we can find these diagonal elements in order of size, so that's quite something. We can rank them straight away. There are algorithms to do that automatically, and all of these sigmas are bigger than 0. So every matrix can be written in this way. Now, why is this so interesting? If you start using your knowledge of matrix multiplication now, you can actually show that that product that we just looked at can be written in a different way. So this is your homework. Okay, see if you can do this. A can be written as a sum of these terms, sigma 1, U1, V1 transpose. This was a little matrix. We looked at matrices like that earlier, plus sigma 2, U2, V2 transpose, and so on. Now, if sigma 1 is big, sigma 2 is still reasonably big, but all these other sigmas that are smaller are too small to really take these terms into account. What we can do is truncate this summation and say A is approximately just those two terms. This is what is used for compression or for finding the principal components of a matrix. And if a matrix is used to store information, we're finding the principal components of the data that we have. And just to finish, I will give you a quick little example of this. Okay, so we quickly go back to the PowerPoint presentation here. Here is a photo that has been expressed as a matrix. We've computed the singular value decomposition or PCA of that matrix. And this is what happens if we approximate that by only a certain number of terms in that summation that I just saw. So a very quick example of PCA. All right, we've reached the end of this first foray into linear algebra. I hope it piqued your interest. I hope you feel like, okay, I should do more, and I hope you will. And thank you very much for joining us, and keep an eye out on future workshops because we'll be offering more in this area. Bye-bye for now.